All right. Good afternoon. Today I'm gonna go over acceleration analysis a little bit. I will talk a little bit about the exam and go over a sample exam, the exam one that we had last year for this course. All right. If we have point P moving along this curve, this is y-axis, this is x-axis. Vector OP representing point P with the distance of r from the center and the angle of theta. So if you want to find x component of P and y component of point P, it's gonna be r cosine of theta, r sine of theta. If you would like to find the velocity of point P, what would be the x component of the velocity, then you should differentiate x of P with respect to time. We represent it with x dot P. So r and theta both are varying with time, because when P is moving along this, the length of r is varying with respect to time. Also, angle of theta is varying with time. So we should differentiate both terms with respect to time. So the derivative of r with respect to time times cosine of theta plus r derivative of cosine of theta with respect to time. This is not going to be 1. R is varying with time. We represent it by r dot cosine of theta minus r theta dot sine of theta. And y component of the velocity, we differentiate this with respect to time, r dot sine of theta plus r omega or r theta dot cosine of theta. Now we would like to find the acceleration. What would be how fast the velocity is varying with time, or what would be the second derivative of x with respect to time, or x double dot. Changing of the velocity, second derivative of displacement, or x double dot, representing the acceleration. We should differentiate velocity with respect to time. R dot is varying with time. It's possible that r dot is varying with time. Theta is varying with time. Similarly here, r theta dot and theta may vary with time. So we should differentiate all terms with respect to time. Derivative of r dot with respect to time, cosine of theta, plus r dot derivative of cosine of theta with respect to time, minus derivative of r with respect to time, theta dot sine of theta, minus r derivative of second term with respect to time, and lastly r theta dot derivative of sine of theta with respect to time. So derivative of r dot with respect to time, we can represent with r double dot. R dot is means changing in the magnitude of the r, and r double dot means how fast r dot is varying with time. So r double dot cosine of theta second term, derivative of cosine with respect to time, it's gonna be negative r dot theta dot sine of theta. We know how to differentiate cosine of theta with respect to time. Here, derivative of r with respect to time is going to be r dot minus r dot theta dot sine of theta. Derivative of theta dot with respect to time, it's going to be the acceleration of theta, angular acceleration, negative r theta double dot sine of theta. And here we have negative r theta dot derivative of sine of theta is going to be theta dot cosine of theta. If I rewrite this again, I'm going to have r double dot cosine of theta. These two are the same, r dot theta dot sine of theta, r dot theta dot sine of theta. So negative 2r dot theta dot sine of theta, negative r theta double dot sine of theta, and negative r theta dot square. So this one has 1, 2, 3, 4 terms for the x component. Y double dot of the p, I should differentiate this with respect to time, something like this. I'm just writing the final results here. R double dot sine of theta minus, is it minus? Plus. Plus r theta double dot cosine of theta minus r theta double dot sine of theta. So these two will be x and y component of acceleration for point P. Any questions so far? So I define 4 terms of acceleration. These two representing 1 term of acceleration, these two representing second term of acceleration, and these two number 3, and lastly this one is representing term number 4 for acceleration. So acceleration of point P is going to have 4 terms. I'm going to look at these 4 terms individually. So this one was point P. If I say x component of point P is going to be r cosine of theta, and y component of point P is going to be r sine of theta. If I define point B with the x component of point B equals to, for example, b cosine of theta, and y component of point B is going to be b sine of theta. If I have these two, point B, and we don't know anything about point B, but we know that the x of point B is going to be b cosine of theta, and y of B is going to be b sine of theta. When you compare these two, the only thing which is different is this coefficient or this length. This one has length of r, this one has the length of b. So this tells me that point P is gonna be somewhere in the direction of point P. So if B is greater than R, B is gonna be somewhere on the top of point P. If B is less than R, then point P is gonna be somewhere here before you reach to point P. But this is what I can get from this information. Now, if I say point C has this negative b sine of theta, y of c, negative c, positive c cosine of theta. Point C has this value as an x component and has this value as a y component. When I compare with point P, I can see this one has cosine of theta, this one has sine of theta. This one has sine of theta, this one has positive cosine. Now, if you look at this and change theta by 90, just add theta by 90, then you can write x of c is going to be positive c cosine of theta plus 90. C cosine of theta plus 90 is going to be negative c sine of theta, and y of c can be written as c sine of theta plus 90, which is c cosine of theta, which is representing this one. So negative c sine of theta is c cosine of theta plus 90, and y is c sine of theta plus 90. So it can tell me point C is going to be somewhere with 90-degree angle from point P. So it's going to be perpendicular to vector OP because the angle is 90-degree offset from theta. And now if point D is negative r cosine of theta, y of D is negative r sine of theta. Both are negative D. The sign for x and y, they have been changed to negative sign. So if I change theta to theta plus 80, 180, and D sine of theta plus 180, I can get these two. So it can tell me point D is going to be somewhere in opposite direction of vector OP. It's going to have 180 degrees offset with point P. All right, back to this problem. Term 1 has these two terms, r double dot cosine of theta as the x component, and y component is r double dot sine of theta. We call this acceleration radial acceleration. R double dot cosine of theta for the x component, radial. Y double dot for radial is R double dot sine of theta. If you compare with point P, you can see cosine of theta, cosine of theta, sine of theta, sine of theta. We can say radial acceleration, vector OP. So this, the first thermal acceleration is gonna be in the same direction of vector OP. Term 2, it has negative 2 r dot theta dot sine of theta, and y of that component has negative 2 r dot theta dot cosine or plus. Thanks. The name of this acceleration is Coriolis acceleration. Coriolis acceleration. If this length is changing as well as theta is changing, we are gonna have this term. So if you compare with point P, here we have positive cosine, here, there, right here we have negative sine, and here we have positive sine, here we have positive cosine. It's gonna be this one. Negative sine, positive cosine. It has 90-degree or it's perpendicular to vector OP. Term 3. Term 3 is negative r x double dot, we call it tangential, so I just represent by t, y double dot t is gonna be negative r theta double dot sine of theta, positive r theta double dot cosine of theta. It's similar to this one, Coriolis. As you see, negative cosine has been changed to negative sine, sine has been changed to the positive cosine. So it is perpendicular to OP, vector OP. And term 4, we call it tangential. Tangential, because it's tangent to vector OP. This one also is tangent, but it has different name. So we call it tangential. And term 4 is going to be this. Usually we call it normal acceleration. X double dot n, normal, negative r omega square or theta dot square cosine of theta, y double dot n, negative r omega square or theta dot square sine of theta. Normal acceleration. Cosine has been changed to negative. Sine has been changed to negative. So it's a 180-degree offset from this vector. So the normal is gonna be in this direction. Sometimes you will see this with A with the index of n, A with the index of c, A with the index of r, radial, and A with the index of t, which represent tangential. So the total acceleration is summation of radial period is what was three? Tangential and normal. So these are all terms of the acceleration that you may see in a motion of point. Suppose point P is moving along this circular path with a constant angular speed. So omega is constant. Which term or which terms of acceleration is going to show up in this problem? If point P, if this curve changes to a radial, a circular path with the omega, constant omega, which terms of the acceleration is going to show up? First one? First one, R double dot. R is not changing. So R dot is not changing. R double dot is going to be 0. Second one, R is not changing, so R dot is going to be 0. Third term, R is, we have R, but theta double dot. Theta double dot is 0 because we have constant acceleration, exactly. We only have normal acceleration. So if you sit the location of P and it's rotating at a constant speed, you will feel some force pointing to the center, which represent the acceleration or normal acceleration. If we have variable speed, if theta dot is varying with time, then term 3 and 4 is shown. These two. Still R dot is not very clear and R double dot also is clear. So this is all you need to know about different terms of acceleration. After the exam, we are going to start deriving the acceleration equation for the standard form of mechanisms, just to show you how we can set up the equation and what would be the unknowns, and we solve those system of equation. Then you know how to do the acceleration analysis for any types of the mechanism, and then we are ready to go to the force analysis. When one mechanism like this, when it's moving, what would be the angular acceleration, what would be the force applied to the slider or any other points of this mechanism. Any question on this? What we did, we just wrote the x and y component of point P. We differentiate to get the velocity, and then we differentiate one more time to get acceleration terms. and we looked at the terms, we could get 4 different terms. And I just introduced these terms. Term 1, 2, 3, and 4. These two, they have the same coefficient. These two, they have the same coefficient. These two, they have same coefficient. And the last 2 terms, they have the same coefficient. So they are representing a vector. These two representing one vector, and these two representing other two. All right. Any question before we move on to the exam? All right. The exam would be on Monday. I will start the exam at 1:10. 1:10 to 2:10. 1 hour exam. It's gonna be on only 302. So let me write.
Did you say Olin 302?
Yes. Let me. So. We will start at 1:10 p.m. So do your best to be there 5 minutes before. It's an open book, open notes exam, so you can bring anything you want for the exam. So
I'm guessing closed device.
pardon?
We can't use MATLAB closed device.
I mean you shouldn't bring the laptop. I mean no laptop
Okay.
is allowed. Just bring the drafting. I mean I may ask you for drafting. Drafting instruments. Calculator. What else? And I think that's it for. Any question about? Yes.
Actually. So last class I asked you if it was just the front and back of the sheet. Did that just changed since the last class?
Yes, I just changed the exam.
All right, thank you.
It's better that to be closed book for you, but
Thank you.
the open book is more not. I don't want to say more difficult, but since you have access to the notes, it's. I can't say more. But if you know how to solve the homework problem, you should be good. I mean, after the exam, I can show you. You have seen this problem in the homework. You have seen this problem on the homework. You should be able to work on those problems. So make sure that you know how to work.
And is there an opportunity for us to get the last homework back prior to the test?
Yes,
Okay.
I do have with me.
Awesome. Thank you.
I just forgot to pass it down. So, any question before I go through the sample exam? All right. Let's look at these exams that I designed for last year. We had exam before the break last year. So first problem is asking to label the links, join, and find the degree of freedom for 4 different mechanisms. You will see the other 2 shortly.
So this is last year's.
Yes, 2017.
Are you
Will you be
gonna?
able to post this? To
Yeah.
I will. I'm just gonna go over them since it's our last class before the exam, here. Open book, open. I should check. I don't know. So can you count the number of links for this? Okay. And for this one, one is ground. This entire handle, I mean, it's one link. Don't count twice because one link is binding. I just think the tricky part of this problem. This point has 3 links connected to one joint. You should count it twice for the joints. 1 link, 2 links, and 3 links. You should count it twice. And here we have 1 pin and 1 slide as one joint. So degree of freedom for this is 1. For this one also is 1. This mechanism, 1 year I asked the students to do displacement analysis for this one, but for last year I just asked find the degree of freedom. That's it's. I mean, the tricky part. I mean, there is one joint here, which is a sliding. So don't count this as a 2 joints because it's not a slider with a pin. It just you remove the pin from this point and added 1 prismatic joint. So count it once. So 1 is ground, 2, 3, 4, 5, and 6. 6 links. How many joints? 1, 2, 3, 4, 5, 1 pin, 6, and 1 slider, 7. It's still 1 degree of freedom. You should just be careful about counting the joint. This is 1 link as a ground, 2, 3. These joints should be counted twice because 1 link, 2nd link, and 3rd link they have been connected to 1 joint. So you should count it twice. So 2 joints here, 1 pin here, another joint as a slider. So 2, 3, 4, 5, 6, 7, 8, and 9. 1 is ground, 2, 3, 4, 5, 6, 7, and 8. The degree of freedom is going to be 3. Any question on this before I go to the second problem? Alright, you are given with crank rocker mechanism. Crank is 2, for example. I mean, here, coupler is 7. Output link is 6 for it. And D is 10. So it's a crank rocker. So you don't need to check if it's crank rocker. It says it's a crank rocker. Means this link can complete 360 degrees. The question is find the input angle in which the transmission angle is 90 degrees. At which theta this transmission angle is 90 degrees. This is the first part of the problem. And after you find that angle, it's asking you find the mechanical advantage of this mechanism when the mechanism is at this position. So if this is gamma, this angle, if this is beta, mechanical advantage, if you remember, was sine of gamma over sine of beta. So gamma is 90, you should find the beta, and then you can find the mechanical advantage. But for the first part, find the input angle in which the transmission angle is 90 degrees. We are just using the cosine rule. Just connect these two points and label this as E. In this triangle, find the length of E, which is going to be B squared plus C squared. B7, C6, you can find E. Now in this triangle, write the cosine rule for theta. So we have A, we have D, I can write A squared plus D squared minus 2AD cosine of theta equals to E squared. You have E, you have A, you have D, solve for theta. Just cosine of theta is gonna be A squared plus D squared minus E squared divided by 2AD and find theta. This is first part. Second part, I need to find beta. This is beta 1, this is beta 2. Beta 1, in this triangle, tangent of beta 1 is C dividing by B. Find beta 1. How can I find beta 2? In this triangle, write the cosine rule for this angle. So it's going to be D squared equals to A squared plus E squared minus 2AE cosine of beta 2. So cosine of beta 2 is going to be this. Find beta 2, and beta would be summation of these two. And then you can find the mechanical.
So do we do the D squared part first there?
After you find
Wait, so E squared.
E, yes, after you find
Right,
E.
yeah. I mean from her too.
Yes. Because why did we use this? Because we want to find beta 2. You always can use the cosine rule in a triangle. In this triangle, you are looking for beta 2. Other lengths are given, you can solve for beta 2. Any question on this?
Is beta 2 the entire angle between them, or is it between E and A?
Between E and A.
Okay.
Because we are going to add beta 2 to beta 1 to get the entire deviation angle. If you remember, we call beta deviation angle.
Is that the mechanical advantage?
So the mechanical advantage was this ratio, sine of transmission angle to sine of over sine of beta. Any question on this? All right, the last problem for this, you were given with an offset slider crank. A, B, C. Yes, offset is C and D. The nouns, as you see, the nouns are A, B. A is 1.4, B is 4, and C is 1. Plus, always we are given. I mean, you have seen this theta 2 were given, and you solve for theta 3 and D. But in this problem, the D is given, the slider position is given. So we are solving for theta 2 and theta 3. The approach would be the same. You write the vector loop equation. Vector loop equation. This is one vector. This is one vector. This and this. Point B, point C, point A, and point D. So vector AB, you reach to the point with 2 arrows ending. So you stop. Put the sign, put the equality sign and go through other path. AB plus DC plus C B. X component would be A cosine of theta 2 equals to AD is going to be D plus DC doesn't have any X component, B cosine of theta 3, A sine of theta 2 equals to C plus B sine of theta 3. And nouns are theta 2 and theta 3. You know how to solve this system equation. First get rid of theta 2, solve for theta 3, then back to this two equation, plug in theta 3 and find theta 2 with matching pair. So, yes?
Since this is an open note, I think the last question would be a multi-mechanism breakup.
It can be.
Oh, yes.
It can be, I mean, but I cannot ask you to work on a long problem because we only have 1 hour. But manage your time. I mean, you only have 6 minutes. I will work on the exam by myself
It takes a
and add anything by factor. If I can do it by 30 minutes, you should be able to do it by 1 hour.
Okay.
With this test,
I should check. I'm not. I don't remember. I don't know. It did not. Was it this or fair?
this is open book open up.
How much harder is it than this stuff?
The first problem is gonna be same as, not same as, but I'm gonna ask you some mechanism.
Same question, essentially, just with
Yes,
different
the first one. Second and third one might be different, but
If like, if you were a weatherman, what would your prediction be for it to be similar? Because, like, let's be honest, a weatherman's prediction is worthless. So if you were to tell us 100%,
Then why ask?
No. If you were to tell us a 100%, you could say that, oh, I didn't actually mean it because I'm a weatherman.
I have no comment.
I believe it. I think he was trying to trick me into telling us.
Any other question? I'll be in my office tomorrow at
Tomorrow when?
I'll be in my office around 9:30.
Because of them.
Or you can shoot me there.
Oh, boy. Oh. It's gonna be a long weekend.
Don't forget to bring the drafting instrument. I may ask you.